Good morning. In today's class, we will learn about backtracking. In previous classes, we have learned about different algorithm design techniques like greedy method, divide and conquer, dynamic programming, and dynamic programming. In greedy technique, by using greedy technique, we solve problem like shortest path and minimum spanning tree, and quick sort and merge sort were binary search were solved using divide and conquer strategy, and all page shortest path traveling salesman problem were solved using dynamic programming. Now backtracking is also one more algorithm design technique. It is a clever form of exhaustive search. The main idea of backtracking is uh, backtracking is a technique used to solve problems with large search space by systematically trying and eliminating possibilities. A standard example of backtracking would be going through a maze. At some point, you may have two options of which direction to go. Now you can see here, this is the maze, and in the initial only we have two options. We have divided this maze into portion A and portion B, whether I have to go to portion A or portion B. So one strategy would be to try going through maze portion A of the maze. If you struck before you find your way out, then you backtrack to the junction. At this point in time, you know that portion A will not lead you to the maze. So you then start back searching in portion B. Now consider, for example, this maze is also a best example for backtracking. As you can see here, initially there are two parts here, portion A and portion B. So if I take portion A and go, I don't find a next route here. So what I can do, I can go back to the original path and continue with the next point. So this type of problem which requires going back to the initial position is called as backtracking. Now you can see here, clearly at junction you could have even more than two choices. Now you can see here in this part of the maze you have three options: portion A, portion B and portion C. The backtracking strategy says to try each choice one after the other. If you ever get stuck, backtrack to the junction and try the next choice. So as you can see here, in this part of the junction there are three options A, B and C. If you stuck in any of the option, you have to backtrack and go to the original position and continue with the next portion. So if you try all choices and never find a way out, then there is no solution to the maze. So we will start with a problem, then you have you will be going through you take one decision and go to some point, and then if you reach the dead point, you get back to the previous one, and again if you reach the dead point, you will get back to the previous portion, and again you continue with the next option, as you can see in this animation here. So when you reach the dead end, you backtrack to the previous thing, and then you see each possible options there, then you go back to the original from where you had started. In this way you find at the last position wherever the solution you will find. In this animation shows you the concept of backtracking. It is you choose any of the solution and then try to reach out. If you don't find the solution at the end, then you get back to the previous one, and again you try to reach some part of the problem. Again if you reach dead end, you get back to the previous one and again start searching for the solution. This part is called as excuse me, this technique of solving the problem is called as backtracking. So, backtracking is used to solve problems in which a sequence of objects is chosen from a specified set so that the sequence satisfies some criteria. And backtracking is a modified depth first search of a tree. It is a procedure whereby after determining that a node can lead to nothing but dead nodes, we go back to the node's parent and proceed with the search on the next child. Here, based on depth first recursive search approach, backtrack test whether solution has been found. If found, return it. Else, for each choice that can be made, make that choice recursive. If recursion returns solution, return it. If no choices remain, return failure, sometimes called search tree. So, how to improve the backtracking? Search pruning will help us to reduce the search space and hence get a solution faster. The idea is to avoid those paths that may not lead to a solution as early as possible by finding contradictions so that we can backtrack immediately without the need to build a hopeless solution vector. There are again two definitions here, explicit constraints and implicit constraints. We will see what it is. Explicit constraints are rules that restrict each xi to take on values only from a given set. Explicit constraints depend on the particular instance of problem being solved. All tuples that satisfy the constraint, explicit constraints define a possible solution space for I. And second definition, implicit constraints are rules that determine which of the tuples in the solution space of Y satisfy the criteria function. Thus, implicit constraints describe the way in which xi's must relate to each other. So, we will see next different terminologies which are associated with backtracking. So, live node, a node which has been generated and all of whose children are not yet been generated. E node, node being expanded, the live node whose children are currently being generated. And dead node, a node that is either not to be expanded further or for which all of its children have been generated. Then depth first node generation. In this, as soon as new child C of the current E node R is generated, C will become the new E node. Then you have bounding function. We used to kill live nodes without generating all their children. Then backtracking is depth first generation node generations with bounding functions, and branch and bound is a method in which E node remains E node until it is dead. Then breadth first search, branch and bound with each new node placed in a queue. The front of the queue becomes the E node. And the depth search, D search, new nodes are placed in a stack. The last node added is the first to be explored. And some of the examples of backtracking are solving a maze, coloring a map, solving a puzzle, and n-queen's problem.